slide. So in case of an asynchronous condition, you cannot transfer the total power. So delta beta equal to 0 means that these are the coupled power and the uncoupled, the power in the two-way guide as a function of the length. So you see that the power decrease arrive to 0 and back again to 1. So the coupled power start to 0, goes to up, 1 and 0. But if you have an asynchronous condition, the coupled power, the maximum coupled power is not 1, but a little bit less. And this depends on how much asynchronous is the coupled.
Phase shift is some coefficient of your K. The coupling
The phase shift, the phase difference between the two outputs.
And it's related to your coupling ratio?
Only for the asynchronous case. I don't give you the expression of the phase, it's not really very important. But for a synchronous case, the phase shift is half pi. J. There is the J here. So it's half pi.
It's 0.
No, half pi.
When it's synchronous.
When it's synchronous. When it's synchronous, the phase shift is half pi. The splitting ratio is K, and the phase, this is real, and this is, sorry, half pi. Always, for every kind of case.
Can you tell me the ratio between the phase shift and the delta beta?
No.
Because delta beta is also your phase.
Why you want to know this relation?
Because I want to see really it's half pi or not.
If it is real, half pi is easy to see. Look at this. What is J? What is J?
It's half pi.
Why?
E to the power of j theta is equal to cosine theta plus j sine theta. So
Excellent. Very good. Very good. Okay. So you can do the same with the more general expression.
I know my question was because I was thinking that the beta is also your phase constant. So when you're saying it's synchronous and the delta beta is 0, but the phase shift is half pi, I was thinking to
I understand
relate it.
No. This is the phase difference between this output and this output. The phase accumulated from the output, from the input to the output, it depends on the total length, depends on the beta, I agree with you.
That one is 0.
But no, this is the number that we are not interested in.
By delta,
and is a common to both.
when you're saying delta beta is 0, you mean there is no dispersion at the end when you have a...
No dispersion, there is no difference. There is no difference between the beta of the two waveguides. Does not mean no dispersion. Dispersion is related to the dependence of beta on the wavelength. The beta 2. So, to be, it's too close to the, sorry. So the phase and the output is something that depends on this length. So is, let's say, phi 0 plus 0, phi 0 plus half pi. And the phi 0 is, if you like to know, 2 pi divided by lambda beta 0 L. So beta 0 is the beta of the waveguide. The average in case of.
Also, the first part is carrying beta 0.
Yes.
Okay.
So, this is the real conclusion of all the formula that we wrote. There is the synchronous case, there is asynchronous case. The Ashisa is the argument of the trigonometric function in your transmission matrix, and you can write the same as a function of the real length. So you see here the synchronous case and the asynchronous case. Obviously, the period change because the argument change. In one case is c, and then the other case is the square root of blah blah blah.
Excuse me, Professor, can you again show which is the asynchronous in the graph?
Asynchronous,
Yeah.
everything except this and this. These are the synchronous because arrive to the top and to the bottom. Okay, this is another simulation of a directional coupler. This is for silicon photonics, so the dimensions are very small, the gap is very small. Here you see the two waveguide are here. So here we enter from here. You see that the mode propagate. After a while, you have light also on the lower waveguide. We continue to propagate. This is the coupling length, or LC or L pi, and you get the maximum transfer of power total because it's synchronous and then go back. These other three simulations tell you in some way how rigorous is the coupled mode theory and where it failed. The difference between this is just the gap between the waveguide. So this is 200 nanometer. The waveguides are far enough. They are coupled, but not strongly coupled. So you see a very nice shape of the mode that continue coupled to this, and but if you started to put them together, close one to each other, the perturbation is higher and higher because gas has the exponential function of the distance, and when you are very close, you see that there is a sort of distortion of the field. Look at this and this. You see here it's not very clean, it's something distorted. This is really the signature of the presence of a very strong perturbation, so the excitation of higher order mode that are radiative, that are leaky, that are not very good. So this is just a slide to tell you that the coupled mode theory works very well, even if the waveguides are quite close one to each other. If they are too close, then you can have losses, you can have a reflection, you can have a distortion of the field, excitation of higher order mode. So do not couple too much.
There is indication. There is indication for its cutoff when the excitation of the other mode appears when they become closer. or we just
There is
The
no
lines.
cutoff condition. You can put the two waveguide, one attached to the other one, but there is no other mode that appears. The other mode that appears are leaky mode, are radiative mode below the cutoff. The perturbation is so strong that you excite this mode, but the modes are not guided, so they go away. But they take a while to go away, no? Some centimeter or millimeter or micro, but they're there. And so you have losses. In effect, if you look carefully, you see that this one is more distorted than this one. It means that you already lost some of the power of this radiation. This is a little bit maybe too detailed to. But it's good.
Is there a standard distance that you use conventionally?
Just a rule of thumb, the width of the waveguide. A little bit less than the width of the waveguide. Clearly depends on the contrast, but also the dimension of the waveguide depends on the contrast. So the gap equal to the width of the waveguide is a good point. I have a quarter of an hour. I can do some exercise, so you are happy. So, yeah. So we want to realize power splitter, so a coupler with a coupling coefficient of 50%. So we have two options. Well, we have many options, but basically two. The first one is delta beta equal to 0. Everyone uses delta beta equal to 0. The transmission matrix is cos CL minus J sin CL minus J sin and cos. So if the product CL is equal to a quarter of pi, the matrix becomes 1 over square root of 2, 1, J minus J, 1. So you enter from here with 1, and you exit with square root of 2. So the power is 1/2 and 1/2. This is called also 3 dB coupler. The output field are in quadrature. Where is the J?
CL pi over 4.
Pi over 4, because pi over 4 means a cosine of 1 over square root of 2 that I wrote here, and also the sine is 1 over square root of 2, so I put the 1 over square root of 2 outside, and inside we have this. So now, if you know your waveguide, so the exponential field outside of the waveguide, so you know C, you can calculate L. So you see, you're not able in the design to calculate L and C, but the two are always together. They appear as a product. So this is your choice. You can do very weakly coupled waveguides, very long, or tightly coupled and very short, or everything in the middle. It is up to the design. It's exactly the same. Well, it's exactly the same at this level. Obviously, the impact of the tolerance of the fabrication process is different. The behavior in bandwidth is different. The behavior as polarization can be different. So a lot of little things. But you always get the product C and L.
Expression why there is one J is minus, the other is not.
Because I forget to put minus. There is another possibility to realize a 50-50 coupler or 3 dB coupler, and it's this one. If we assume that delta beta, if we assume that square root delta beta to the square divided by 2 plus 4, the C plus multiplied by L is equal to 1/2 pi. If we assume this one, the transmission matrix of the asynchronous coupler, because this is asynchronous, with assume delta b equal to twice the coupling coefficient, we get this. J delta beta C minus G minus J delta beta C. And becomes, with this condition, J 1 over square root of 2, 1, 1, 1, 1, minus 1. Okay. So you take the general expression of the matrix, transmission matrix, in the asynchronous case. You impose the argument of the sin equal to 1/2 pi. Then you get this matrix, but you want a 50-50%, so you want this one equal to this. So you have delta beta equal to 2c. So everything becomes equal to 1, and you have this term in front. So you see the two matrices from the intensity point of view are exactly the same. So both split in two. The only difference is the phase of the output. The two outputs are in quadrature here, and here are in phase.
I think there is minus before j over square root of 2 because if together minus j.
Probably yes. So the condition in this case is this one. This is the length, and this is the coupled power. This is 1. So we have the cosine and sine function, and we are working here. This is the length of our coupler. So we get a 50-50% condition. In the other case, instead, is this. There is no total transfer power because it's asynchronous, and we are in this condition. We are working here. So both realize a splitter. One is synchronous, the other one is asynchronous. Which one is the best? Well, you should ask me, what does it mean best? Best in which sense? No? You say that one because the two waveguides are equal. And which is the advantage of have the two waveguides equal?
You say it's a cascading, known the phase when you cascade.
So you don't have to change the dimension of the waveguide. So you avoid the taper, you avoid the change of width. This is a good reason. This is why people use that solution. But think to the technological process, and you make an error in the gap in the dimension. No? So if you make an error here, you get a strong variation of the coupling coefficient. Here you are on a maximum, and so if you make an error here, it's very reduced the error. So this is more robust with respect to the technological tolerance. This is less robust. So this is just to add some confusion. This one is best, but everyone use this one. Okay? Because life is not so simple. There are many reasons behind them. Okay, another example, another exercise. We want to make a switch. we want to make a switch, so we enter from here. We have the coupling coefficient C and the delta beta equal to 0. So the length of the coupler is LC equal to pi divided by 2C. So all the light come out from this port. 100% coupling is a synchronous coupler, so nothing special. You know. It's this. Now we want to switch the output from this port to this port. How can we do it? If we are able to change one of the waveguide, so induce a delta beta, so you perturb only one of the waveguide of the coupler, you induce a delta beta, you move from the synchronous coupler to the asynchronous coupler. In this case, the coupling length or pi length is given by pi divided by 2 square root of delta beta square divided by 4. The expression is a little bit more complex, and it's this one. So let's draw the condition here. L1. Okay, so with the synchronous one, we are in this condition. So we are here. If you perturb one of the waveguide, you add the delta beta, you don't change the coupling coefficient, C is always the same, it means that you are decreasing the coupling length. And what you want is this. So you wanted to half the coupling length. So you can move from one waveguide to the other. The coupling is no more 100% because it is asynchronous, and you wanted to reduce by 1/2 the coupling length. So if LC0 is the coupling length of the asynchronous, now we want LC equal to 1/2 of LC0. So we have to compare the two, impose this condition, and what we get is pi divided 2c to the square, that is this one, equal to 1/2 of this, 1/2 of this. So is pi divided by delta beta square divided by 4 plus c to the square. This is to the square, and what we get is delta beta equal to square root of 12c. A strange number, but you can calculate is this 4 by this. And what you get, so you have to perturb the waveguide, one of the waveguide, only one, because you want to move from the synchronous to the asynchronous. So you perturb only one waveguide by this quantity in order to divide by 2 the original coupling length and move from cross to this condition.
So yeah, I got confused. We enter from here to here, and we want to switch. So I enter from the first.
Then you enter from here, and you want to get out from here.
So if I reduce it to a half LC, I will be in the middle. I will have to 50-50.
No, because with the asynchronous condition, this is the periodicity. It's faster. You get this an entire period, while before you get only this. So you move from here to here. You must be able to touch only one waveguide. Maybe it's not easy, but it's possible to do.
What is under the root? Under the square root is square.
12, yes.
Thank you.
From this, this is 55.
How I change the beta? How I change the beta?
How? This is a technological problem. With an electric field, with a thermal field. In practice, typically is both or thermal field by heating just one waveguide, or with an electrical field in case of an electro-optic material.
I turn it on one point if I have the whole beta equal symmetry, and then I prefer just one of them to.
Yeah. Yes. Neat. Say you have some coupling, so the light go down a little bit and then go up. Yes, this is a switch. You can change as you like. So tomorrow we go back to the directional couple. Maybe we do another couple of exercises, and we continue with other kind of. Thanks. Have a nice day.